Ever think about, like, I don't know, a surface so flat, so smooth, that you'd need, like, a microscope to see any imperfections? I mean, we're talking tolerances measured in, what, millionths of a meter? You might be working on projects yourself that need that kind of insane precision. Or maybe you're just someone who geeks out on how they even make stuff that perfect in factories.
It's mind-blowing, right?
Totally. So today we're going deep on CNC surface grinding machines.
These things are the heavy hitters when it comes to making surfaces that are flat, like unbelievably flat. Forget your grandpa's hand grinder. This is high-tech automation.
We did a ton of research for this.
Yeah.
Really dug into how these machines work, all the nuts and bolts.
Literally.
Yeah. Our goal today is to figure out that how do they get such crazy accuracy? And the why are these things so important in industries like aerospace, where a tiny flaw can mean, well, disaster?
Can't have a wing falling off mid-flight because of a bumpy surface.
Exactly. So
Eh.
let's start simple. What is a CNC surface grinding machine, and what problem does it solve that other tools can't?
Okay, so picture this. You're trying to make a surface that's perfectly level, no bumps, no dips, across the entire thing. Now, regular milling machines, they can get you pretty close.
Right, like the ones with the spinning cutting tools.
Yeah, exactly. But getting to that final ultimate flatness and the right kind of surface texture, it's incredibly difficult. You could do it by hand, but
That'd take forever.
and it'd be inconsistent, especially if you need thousands of identical parts. Like, imagine hand polishing every iPhone screen. No way.
Talk about a repetitive strain injury.
Right. So the CNC surface grinder is like the superhero of flat surfaces. It's this automated machine that uses a spinning abrasive wheel, basically, a super precise grinding wheel, and it's guided by a computer. This wheel carefully shaves off tiny bits of material.
So it's like meticulously sanding it down.
You got it. And what you're left with is a surface that's incredibly flat, often parallel with other surfaces on the part. And the finish, it's super smooth, almost like glass.
So where would you actually use something this precise?
Oh, all sorts of places. Think tool rooms, where they need perfectly shaped tools. Or mold making, where the mold surface determines how the final product looks. And any production line where things need to fit together perfectly, like an engine block, where those surfaces need to be flawless to seal in all that pressure.
So we're talking about, like, the final touch, the finishing step for super important parts.
Exactly. This is like the high-end spa treatment for metal parts.
I love that analogy. All right, so we can kind of picture this machine, the wheel spinning, metal shavings flying. But how does it actually make something so flat? What's the secret behind that?
The magic lies in the movement, in the way it's controlled by the CNC system. So the workpiece, the thing you're grinding, it's clamped down on a table. This table moves in a very controlled way. At the same time, the grinding wheel, it's following instructions from a computer program, something called G-code. It moves back and forth over the workpiece. And here's the key. With every pass, it takes off a tiny, tiny layer of material, bit by bit.
Like a super precise cheese grater.
Kinda, but way, way more precise. We're talking about microns, like a thousandth of a millimeter.
Wow. So it's all about this coordinated movement, right?
Absolutely. The table moves in one direction, the x-axis. The grinding wheel moves across it, the y-axis, and then the magic, the z-axis. That's the vertical movement, where the wheel dips down a tiny bit after each pass. The CNC controller, it's like the brain, orchestrating every movement down to the tiniest fraction.
It's like a ballet with every step perfectly timed.
A very high-stakes ballet. So imagine it. The workpiece moving back and forth, the wheel zipping across, and then just a hair's breadth downwards. Repeat, repeat, repeat until you've got that flawless surface.
It's incredible how they program that kind of precision, but why go through all that trouble with automation? Why not just have a skilled machinist do it by hand?
Well, with automation, you eliminate the risk of human error. Every single movement is exactly as the program dictates, perfectly repeatable. Plus, it's way faster, especially for complex shapes or when you need a ton of parts. Imagine trying to hand grind 1,000 engine components. That'd take forever.
So it's about consistency, speed, and that incredible accuracy.
Precisely. You get parts that are within tolerances that are frankly mind-boggling. And it's not just finishing touches. These machines can really hog off material, making them suitable for making parts like crankshafts, even those huge molds for injection molding.
Okay, so the CNC controls the movement, but what about the actual grinding part? What kind of wheels do these things use? It can't just be a simple sharpening stone, right?
You're right. It's way more complex than that. The grinding wheel is like the heart of the operation, and there's a huge variety to choose from. Each one is designed for a specific material and a specific task.
I can imagine picking the wrong one would be bad.
Oh, you know it. The wrong wheel could give you a terrible surface finish, slow down the whole process, even burn the workpiece, ruin the wheel itself, or make things downright dangerous.
So how do you even begin to pick the right wheel?
Several things to consider. The most important are, what's the wheel made of the abrasive material? How are those abrasive particles held together, the bond type, the shape and size of the wheel, and how coarse or fine the abrasive is, the grit size. All these depend on what you're grinding and what kind of finish you need.
Let's start with the abrasive. What are some common ones?
A very popular one is aluminum oxide, a workhorse for various steel types. Then you have silicon carbide. It's harder and great for cast iron, non-ferrous metals like aluminum or brass, even some ceramics. And for super hard materials like hardened steel or carbide, you need super abrasives like cubic boron, nitride, CBN, and diamond. These are basically the Chuck Norris of abrasives.
Makes sense. You need something extra tough for those tough materials.
Right.
And you mentioned grit size. What does that mean?
Grit size tells you how big the individual abrasive particles are. Basically, it's a trade-off. Bigger grit, faster cutting, but rougher finish. Smaller grit, slower cutting, but smoother finish. Like a low grit, say 80, will hog off material, but leave a rougher surface. A high grit, like 120 or more, takes its time, but gives you a super smooth finish.
So it's like sandpaper. The lower the number, the rougher it is.
Exactly, and most general work uses a grit somewhere between 80 and 120, a good balance.
And what about wheel shapes? I always think of a flat disc. Are there others?
Oh yeah, tons. The straight wheel is the classic, but you've got cup wheels, good for large flat surfaces where you need even pressure. Dish wheels are great for sharpening tools or grinding in tight spots. And then there are all these weird and wonderful shapes for specialized tasks like form grinding where you need to make a specific profile.
So basically a wheel for every occasion.
You got it. And modern grinding wheels are incredibly efficient. They can remove way more material than the old ones. So these CNC grinders aren't just for delicate finishing anymore. They can do serious heavy lifting in production environments.
That's pretty amazing. I think you even made a table to summarize all these wheel types, right?
I did. Here it is. First column is wheel abrasive, aluminum oxide, silicon carbide, ceramic alloxide, CBN, diamond. Second column is typical materials ground. Steels, cast iron, aluminum, brass, ceramics, hardened steels, difficult alloys, very hard steels, carbide, ceramics. Third is common grit range, 46, 120 plus 6120 plus ferrins, 6120, 100 plus mesh size. And the last column is notes. Most common general purpose, good for brittle non-ferrous, tougher, longer lasting AOI bars, super braces for extreme hardness.
That's super helpful. Thanks. Now, we've talked about the wheel cutting, but what about the part being cut? How do they make sure it stays perfectly still while all that grinding is going on? There must be a ton of force involved.
You're sharp to pick up on that. Grinding does create a lot of force, and if the workpiece moves even a little, you lose that perfect flatness and accuracy. Even a tiny vibration can mess things up, so holding that workpiece rock steady is crucial.
So how do they do that? Glue it down.
Not quite. For parts made of iron or steel ferrous metals, the most common method is electromagnetic chucks. They're built right into the machine's table.
Magnetic chucks. That makes sense for metal. How do they work?
These chucks have strong electromagnets that you can turn on and off. When they're on, they create a powerful magnetic field that sucks the workpiece down onto the chuck, holding it tight and flat. No slipping, no wobbling, just pure stability.
But what about parts that aren't magnetic, like aluminum or plastic?
Good point. Magnets won't work on those. So for non-ferrous materials, you need different tricks. Mechanical clamps are common, like vices bolted to the table, or custom-made clamps shaped to hold the specific part. Sometimes they even use vacuum chucks that suck the part down.
So a whole arsenal of holding techniques.
But it's not just about the clamps. The machine itself needs to be super rigid. The base, often made of a special cast iron called mehanite, it needs to be heavy and strong to absorb vibrations. And the guideways that the table moves on, they need to be super precise and smooth. All this ensures that even the tiniest movements are accurate.
It's like a surgeon's steady hand. The tool's only as good as the platform it's on.
Exactly. Now, another thing to think about with grinding is all the sparks and heat. Do these CNC grinders use coolant, like cutting fluid, during the process?
Yeah, it seems like it'd get pretty hot in there.
It absolutely does. Grinding creates a lot of friction, and that generates heat. So you're right to think about coolant. It helps keep things cool, but sometimes you don't want coolant, it can mess things up. Knowing when to use it is key.
So is it usually a wet or dry process?
Most of the time, CNC surface grinders use coolant. We call that wet grinding. That has a lot of benefits. but sometimes you need to grind dry depending on the material or the job.
Okay, let's talk about wet grinding first. What are the advantages?
Well, first and foremost, cooling. That grinding action creates a ton of heat where the wheel touches the workpiece. Coolant whisks that heat away, preventing the part from overheating. Too much heat can burn the metal, warp it, or even change its hardness.
Plus, I bet it helps the grinding wheel last longer, too.
Absolutely. Second, coolant washes away the tiny metal chips and abrasive particles created during grinding. We call those swarf. Those little bits can scratch the newly ground surface or clog up the wheel, making it less effective. So coolant keeps everything clean.
So it's like a tiny shower for the workpiece. Are there other benefits?
You bet. Coolant can also lubricate the grinding process, reducing friction between the wheel and the workpiece. That makes for smoother grinding, a nicer finish, and maybe even save some energy. And a lot of coolants have rust inhibitors, which protect the machine and the workpiece from corrosion.
Sounds like coolant's got a lot going for it. What types are there?
There are oils, water-based emulsions, synthetics, sometimes even thick pastes or gels. It all depends on the material, the wheel, and the desired finish.
You mentioned dry grinding earlier. When would you choose that?
Few reasons. Some materials, like magnesium, react badly with water-based coolants, so you have to grind dry, often with special dust extraction systems. Also, some ultra-clean environments, like in electronics manufacturing, can't have any coolant residue. And some specialized processes, especially with super abrasive wheels, might need to be done dry, although coolant is still often preferred if you can manage the heat.
So, for most metal parts, the rule is,
If you want a top-notch finish and accurate dimensions, coolant is your friend. It helps manage heat, keeps the grinding clean, and protects your equipment and the workpiece.
you've got another table for us summarizing this, right?
Always. Let's see. Condition. General steel grinding, hardened steel grinding, high precision work, magnesium alloy grinding, ultra-clean applications, cast iron grinding. Reason. Heat chips finish, prevent thermal damage, flush fine chips, material reacts, avoid residue, chip flushing cooling. Coolant use, yes, wet, yes, wet, yes, wet, no dry, possibly no dry, yes, wet. Coolant types often used: emulsion synthetic soils, filtered synthetic soils, NA synthetics emulsions.
I really lays it all out, thanks. So for our listeners, what we've learned today is that CNC surface grinders are these amazing machines that use computer control to create unbelievably flat and precise surfaces on a huge range of materials.
And it's a combination of things that make it work. The right grinding wheel, rock-solid work holding, and usually some carefully chosen coolant.
It's pretty mind-blowing when you think about the level of precision involved. We're talking about removing material just a few microns at a time.
Yeah, like shaving with a laser.
Huh. It makes you appreciate all the hidden complexity behind everyday objects. You know, we take it for granted that our phones are perfectly smooth or that engine parts fit together with microscopic precision. It makes you wonder what other seemingly simple processes actually involve this kind of intense engineering and material science wizardry.
It's a rabbit hole worth exploring.
Definitely something to ponder.